Hi guys, welcome back to our discussion on infinite series. So in this video, we'll talk about Taylor polynomials and approximations. So before we start, let me discuss the objectives of the study. So at the end of this lesson, you should be able to find polynomial approximations of elementary functions and compare them with the elementary functions. And then second, find the Taylor and the Maclaurin polynomial approximations of elementary functions. Okay, so in this discussion, we start by finding a polynomial function p that approximates another function f na by choosing a number c in the domain of f at which f and p have the same value, that is p of c equals f of c. The approximating polynomial is said to be expanded about c or centered at c. And geometrically, if you can recall, in analytic geometry, one of the requirements that p of c equals f of c is that the graph of p should passes through the point c, f of c. Of course, there are many polynomials whose graph pass through the point c and f of c. So your task here is to find a polynomial whose graph resembles the graph of f near this point. So one way to do this is to impose the additional requirement that the slope of the polynomial function be the same as the slope of the graph of the function f at that point c and f of c, such that p of c must be equal to f of c. So as you can see here in this figure, this is your p and this is the given function. So there's this one point c and f of c where p of c is equal to f of c, and the first derivative of the function f prime of c is equal to the first derivative of the polynomial function p prime of c. Okay, like for example, for the function f of x equals e to the x, we need to find a first degree polynomial function denoted by p sub 1 of x equals a sub 0 plus a sub 1x, whose values and slope agree with the value and slope of the function at x equals 0. So in this case, because the given function is e to the x, or f of x equals e to the x, and we know that the first derivative of this function is e to the x. Okay, the value and the slope of the function at x equals 0 can be obtained by substitution. Okay, when x equals 0, so the value of the function at 0 is e to the 0 or 1. And the value of the first derivative at 0 is also e to the 0, which is equal to 1. So this one here is the value of f at x is 0, and 1 here is the slope of the function at x equals 0. Okay, because the function p sub 1 of x is a sub 0 plus a sub 1 of x, when you get the first derivative, now we get p sub 1 prime of x is equal to, this is 0, so we have a sub 1. Then at x equals 0, the value of the function at 0 is, by substitution, is a sub 0 plus a sub 1 times 0. But because this is 0, so the value of the function at 0 is a sub 0. Also, the value of the first derivative at 0 is equal to a sub 1. But from the definition, um, the polynomial function p sub 1 of x is equal to f of x, and at x is 0, we can conclude that p sub 1 at 0 is f at 0 is equal to 1. So therefore, because p sub 1 at 0 is a sub 0, so a sub 0 is equal to 1. Also, the first derivative of the function at x is f prime of x, and at x equals 0, the value of the first derivative of the polynomial function at 0 is equal to the value of the function at 0, and we know that this is equal to 1. But since the value of the first derivative at x equals 0 is equal to a sub 1, so we can conclude that a sub 1 equals 1. So therefore, The approximated polynomial function is defined as p of x is a sub 0 plus a sub 1x, where a sub 0 is 1 and a sub 1 is 1. So we have 1 plus x. Okay, next we go to Taylor and Maclaurin polynomials. For expansions about an arbitrary value of c, it is convenient to write the polynomial in the form of p sub n of x is a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c to the second power plus a sub 3 times x minus c to the third power plus and so on and so forth plus a sub n times x minus c to the n power. So in this form, repeated differentiation produces the following: that the first derivative of the polynomial function of nth degree at x is a sub 1 plus 2a sub 2 times x minus c plus 3a sub 3 times x minus c squared plus and so on and so forth up to plus n a sub n times x minus c raised to n minus 1. Then the second derivative of the nth degree polynomial p sub n of x is 2a sub 2 plus 2 times 3a sub 3 times x minus c and so on and so forth up to plus n times n minus 1 times a sub n times x minus c quantity raised to n minus 2. And so on and so forth up to the nth derivative of p sub n of x, which is equal to n times n minus 1 times n minus 2 and so on up to 2 times 1 times a sub n. Okay, letting the value of x as c, then we obtain the following values. P sub n of c is a sub 0. First derivative of p sub n at c is a1. Second derivative of p sub n at c is 2a sub 2 and so on up to the nth derivative of p sub n at c is n factorial times a sub n. So because the values of the function starting from the function up to the nth derivatives agrees with the values of this polynomial function and its first n derivatives, then it follows that the value of the function at c is equal to the value of the polynomial function at c, which is a sub 0. The first derivative of the function at c is a sub 1. The second derivative of the function at c over 2 factorial is a sub 2, and so on up to the value of the nth derivative at c over n factorial is equal to a sub n. So with this coefficient, you can obtain the following definition of Taylor polynomials named after the English mathematician Brooke Taylor, and Maclaurin polynomials named after the Scottish mathematician Colin Maclaurin from 1698 to 1746. Okay, so let's now define the Taylor and the Maclaurin polynomial. So by definition, if f has n derivatives at x equals c, then the polynomial p sub n of x is equal to f of c plus the first derivative of the function at c times x minus c plus the second derivative of f at c over 2 factorial times x minus c to the second power plus and so on and so forth up to plus the nth derivative of f at c over n factorial times x minus c to the n power is called the n-Taylor polynomial for f at c. But if c is equal to 0, then this polynomial function p sub n of x is equal to the value of the function at 0 plus the first derivative of the function at 0 times x plus the second derivative of the function at 0 over 2 factorial times x squared plus the third derivative of the function at 0 over 3 factorial times x cubed plus and so on and so forth up to plus the nth derivative of f at 0 over n factorial times x to the n. So this is called the nth Maclaurin polynomial for f. Okay, so in this example, given the function f of x equals e to the x, so we need to find the Maclaurin and the Taylor polynomial. For the Maclaurin polynomial, the first thing that we have to do is we need to differentiate the function. So given this function f of x equals e to the x, so the first derivative denoted by f prime of x is e to the x. The second derivative of the function is e to the x, and so on up to the nth derivative of f of x is e to the x. So to find the Maclaurin polynomial, we need to find the value of the function and also the nth derivative or the first nth derivative of the function at x equals 0. So when x is 0, the value of the function at 0 is e to the 0 or 1. Then the value of the first derivative at 0 is also e to the 0, which is 1. And so on up to the nth derivative of the function at 0 is also equal to 1. So we can now define the Maclaurin polynomial from the definition as p sub n of x is the value of the function at 0 plus the value of the first derivative at 0 over 1 factorial times x plus the value of the second derivative at 0 over 2 factorial times x squared plus and so on and so forth plus the value of the nth derivative at 0 over n factorial times x to the n. Okay, and then by substitution, this the value of the function at 0 is 1. So p sub n of x is 1 plus the value of the first derivative at 0 is 1. So you have 1 over 1 factorial also 1, or 1 times x. So we have x as the second term. Plus the value of the second derivative at 0 is also 1 times x squared all over 2 factorial. So we have 1 over 2 factorial times x squared. And so on and so forth up to the value of the nth derivative at 0 is also 1 over n factorial times x to the n. So this is called the Maclaurin polynomial for this function f of x equals e to the x. And how about the Taylor polynomial, say centered at x equals 1? Okay, so at x equals 1 and or at c equals 1, then the polynomial, the Taylor polynomial denoted by p sub n of x is equal to the value of the function at 1 plus the value of the first derivative at 1 over 1 factorial times x minus 1 plus the value of the second derivative at 1 over 2 factorial times x minus 1 to the second power plus the value of the third derivative of the function at 1 over 3 factorial times x minus 1 to the third power plus and so on and so forth plus the value of the nth derivative of the function at this should be at x equals 1 all over n factorial times x minus 1 to the n power. So by substitution, because the value of the function at x equals 1 is e, so this should be e plus the value of the first derivative at 1 is also e. So we have e over 1 factorial times x minus 1 plus the value of the second derivative at x equals 1 is also e times this one is x minus 1 to the second power all over 2 factorial, and then plus if plus the value of the third derivative of the function at x equals 1 is also e times x minus 1 to the third power over 3 factorial plus and so on and so forth plus the value of the nth derivative at c is equal to 1 is also e times x minus 1. This should be to the n power all over n factorial. Okay, so in summary, to approximate the Taylor and the Maclaurin polynomial, okay, this definition must be followed that if f has n derivatives at x equals c, then this polynomial denoted by p sub n of x equals f of c plus the first derivative of f at c times x minus c plus the second derivative of the function at c over 2 factorial times x minus c to the second power plus and so on and so forth up to plus the nth derivative at c over n factorial times x minus c to the n power is called the n-Taylor polynomial for f at c. So if c is equal to 0, then the Maclaurin polynomial denoted by p sub n of x is equal to the value of the function at 0 plus the value of the first derivative at 0 times x plus the value of the second derivative at 0 over 2 factorial times x squared, plus and so on and so forth up to plus the value of the nth derivative at 0 over n factorial times x to the n power.